Right. Okay, sorry for the interruption. Let's continue. So I think actually it is not as much like, it's not as complicated as I thought, because if you have some element which is in, let's say, so the mapping is from V to W for both T1 and T2. So let's say there is some V which is in the kernel of T1, but not in the kernel of T2. And that's the situation we want to avoid, right? Because supposedly that the kernel of T1 is a subset of the kernel of T2. So how do you avoid such a situation? Through this use of another linear transformation S from V2 itself, right? Then what you could do is you could take S and map it to an element which is not in the kernel of T1. Or sorry, no, what am I doing? No. No. Should. Oh no, that's my bad. Yeah, sorry. No, S is a map from W to itself. So you want to, so if V is in the kernel of T1, then T1 of V will be 0. But you want to map from 0 to a non-zero element is probably what you will want to do. That seems to be the case. Let's say V is in the kernel of T1, but not in the kernel of T2. Oh, sorry, what am I doing? This is completely not what the proof is about. We want to show that if the kernel of T1 is the subspace or subset of the kernel of T2, then there is this linear transformation S such that T1, T2 is equal to S composes T1. Right. So what you want to do is, so T1 has a null space, which is supposedly a subset of T2. So you want to expand using this S to expand the null space. Right? You want to expand the null space of T1, right? Maybe draw a better diagram. That's not a very good diagram. So if you have a mapping from V to W, and this is T1, then another S will map some more elements to 0 than before, right? That's probably what you want. Oh, it's the same 0 anyways. Yep, this is probably what you want. So the act of adding this S effectively enlarges your null space in V, right? Because then the kernel of ST1 is the same as the kernel of T2. And the kernel of ST1 is bound to be larger than the kernel of T1 itself, because S, through some sort of remapping like this, allows more elements of T to be mapped to 0 in the end. right? So you probably want to design it so to target all the elements which are in the null space of T2. All the elements which are in the null space of T2, but is not in the null space of T1, right? Because eventually you want those two null spaces to be equal, that of ST1 and T2. But right now T1 has a smaller null space than T2, so you use S to map those extra elements which are in the null space of T2 but not in the null space of T1 to 0 as well. So if you draw a nice diagram, then what you want to do is, like, if this is the null space of T1 and this is the null space of T2, then those extra elements which didn't map to 0 for T1, you want to remap to 0 using S. That's simply constructed so that for such V, S of V is equal to 0, right? Or rather, S of T1V is equal to 0. Maybe to formalize that phrasing a bit more, what you want to say is this: for all W and W such that the transformation of V, the linear map of V T1 on W, the linear map of T1 on V is W, where is inside the kernel of T2 but not kernel of T1. What you want to do is S of W equals to 0, right? But probably want to put some exists V, because the mapping from V to W may not be surjective and you may miss some W's there. But for all W's where there doesn't exist a V such that this is true, with V's in the kernel of T2 but not T1, you just want to map it to the identity, I think, because kernel of T1 will be preserved in that way, because if you already map to 0 in W, then that's fine, because S of 0 is still 0. So that preserves the kernel of T1 while mapping the kernel of T2 elements that are in the kernel of T2 but not T1 also into 0 as well. So I think that's a reasonable argument to construct S. There might be something going the other way around which makes it easier, I suspect, but I'm not sure. So you already have this S, so that T1 is equal to T2S. Then what you're looking at is something like this, right? So T1 maps some things to 0, and then let's say S maps some other things to 0, right? Or that's the next question, actually. This is T2 and S composes T1, right? Let's say this is T1 and this is S. Then what you gotta think about here is the fact that you gotta show that no space of T1 is in fact a subset of no space of T2, and the way to show that is for every element which is in the null space of T1 is also in the null space of T2, right? And I think that's very definition oriented, because if some V is in the null space of T1, if it's in here, then obviously it'll map to 0, right? So maybe I shouldn't use the word obviously. Whenever the professor used it, I get annoyed. Because sometimes things that are said in math are not always obvious to everyone, and that people at different levels to things. So T1 of V is equal to 0. So then T2, which is nothing but S composed with T1, is going to be 0 as well, because it's going to be S of 0, right? So anything which is in the kernel of null space, anything that's in the kernel of T1 will obviously, well, I keep saying obviously, it will also be in the kernel of T2, right? Because T2 is just S composed with T1. Now that side, I suspect it was going to be easy because S was already constructed for you, and the way you approach that was very definitional, using definition of a null space, right? So suppose V is finite dimensional, and this is a very similar question talking about the range. So notice how 22, 23 are paired against each other, and 24 and 25 are in the same way paired against each other, as a way for you to get familiar with null spaces and ranges, which I think I am right now. So show that range T1 is a subset of range T2 if and only if there exists that construction. So first we're gonna go this way again. So we know that range of T1 is inside the range of T2, and then we're just going to show that you can construct an S going from V to V, so that T1 is composed, T2 composed with S. So first off, you want to draw like a mental diagram of this once again. This time you gotta go from V to V first using S, and then go from V to W using T1, right? So think about it this way, I think. If T1 previously mapped to, so the fact that we know that range of T1 is a subset of the range of T2 tells me that maybe previously the inputs of T1 has been changed in such a way that they only map to what's already being mapped to in range of T2. And what I mean by that is maybe S restricted the input of T2 in such a way that oh, right, that doesn't make sense. So if S gets to modify the input first, it should restrict what is mapped to by T2, right? So in fact, T2 composed with S having the same mapping as T1 means that T2 originally was going to map to much more, but since S restricted it, now it's on the same level as T1. I think that's what's going on. That's kind of a weird thing to think about. Yeah. So yeah, that was not the best diagram. Gotta redraw that. So consider you have V, and W. Originally, T2 was going to map to more of W. Then compared to T1, maybe T1 was just going to map to like a super small section in W. But then S restricted the inputs that were allowed in such a way that only this small bit of V was allowed to be mapped at all, because everything else got directed to it. And then now it's only like a small subset of the range that it used to have. Which I think that's a very comparatively intuitive picture of what went on there. So, but in terms of the construction of S, we want to once again target any element V perhaps which is in the range of T2 but not range of T1, right? If it's not in the range of T1, then we want to restrict it somehow. And I think this is not so bad. So assume for such a W there exists a V such that T2 V equals to W, right? And this must exist for the reason that W is in range of T2, right? And then what you do is just map such a W to 0 first using S. So what it will look like is probably something like this. So this V will map all those things to 0. And the rest of the things will get mapped normally. Right, so previously if those things were mapping to some W's that were not in range of T1, then you just want to map them to 0. So then they get squished, right? I think that's quite reasonable. But almost like a floor function or something like that, you want to do a piecewise function definition, where if this is the case, then S would be equals 0. If it is not the case, then you just want to use the identity function once again. I think that's a fair statement to say. This is a construction of S, so that this will work. But you want to go the other way around. So let's say T1 is equal to T2S. Then you want to show range of T1 is less, or a subset of range of T2, right? So once again, we want to show for every element of range of T1 is also an element of range of T2. I think it's fair. So consider some arbitrary element of range of T1, right? And then you have to somehow demonstrate that it's also in the range of T2. But since it's in the range of T1, it must be also in the range of T2 composition of this S. Somehow, then what needs to be shown is that it's also in the range of T2. Oh, wait, this is not even the right. Okay, yeah, this is why. Because it's really the range of T1 and T2 are in W, so I should be talking about W's. I mean, technically you can use the variable V, but that just previously, as I have written, betrays a lack of understanding, right? Yeah, so this is probably more accurate if you think about it. So then what you have here is W is a member of the range of T2 composed of this S, because these two statements are established by this equality, and then you have how do you go about this? Well, let's try to do a counterexample. If W is not in the range of T2, then could it be in the range of T2 composed with S? And I don't think it could. The reason is because if it was not in the range of T2 to begin with, there's no way you can. So there's no way that T2 composed with S, which S is just keeping things in V, right? Will suddenly map to something that T2 itself wasn't able to map to before. So if W is not in range 2 exists, let's say V in V such that T2 would be S not equal, it's not in range T2, which doesn't make sense, right? Now of course this V is let's say S of V2 equals V. I won't go like backwards to show that because also that's probably better. Like there's a more logical way to do that, but I think that's sufficient for a YouTube video. Let's say D is a linear map from the set of all linear maps from polynomials to polynomials, such that it's the derivative map basically. So show that this map is surjective, right? And previously, I was thinking about this while I was walking to school, and it's a long walk to go to anywhere in the school, but it didn't make sense to me because I was like, what the heck is this, right? How can you prove something is surjective just from a degree formula? This is extremely vague. And then I reminded myself after a very long while thinking that this is linear algebra. One of the coolest things you can do is multiply everything by a constant, and it still works. And so what you could do is, and you're over a field, right? Anytime you're talking about a vector space, you're operating on a field. You can take multiplicative inverses and you can multiply by constants, and you can do pretty much lots of things like that. You can span and all that. Before I confuse you any further, let me show you what I'm talking about. So consider the case where you have let's say a degree 1 polynomial, right? And what this derivative map will take it to is the space of constants, right? So it doesn't matter what polynomial of degree 1 you have there. If you take a derivative, it's going to lead to you having a constant. You have x, that's going to give you 1, 2x is going to be 2, and so on. And it doesn't exactly matter which polynomial you took a derivative of, because then you can take a multiplicative inverse of it in the field to get 1. And then from there, you can cover the entire field. The entire space of constant, right? But it probably doesn't need to be that difficult to begin with, so you probably want to do is just settle down for a nice derivative of x, right? This will get you to 1, which will, if you want to get other constants, for example, you want to get a constant c, by the linearity of linear maps, I guess, you can multiply by c of that degree 1 polynomial to get the derivative of it to cover that c in the constants. And so it does, so you found a way to cover all members of the field of, or all members of the vector space of polynomials at degree 0. So then what about degree 1, right? Ideally you want to think in terms of degree 2, but it's a bit complicated. So let's say degree 1, you are spanned by the bases of 1 and x, right? Then we know all the ways to construct this 1, but then this x is very similar. You just do it from x squared. Derivative of x squared is 2x, so you probably do is do half of x squared, right? So then this will allow you to generate another element of the basis of degree 1. So probably what you want to do is probably something that looks like this. If you take a derivative of this will map, the linear map from this will go to this, let's say. And then from here you can scale up and down, right? So depending on which polynomial you want in the output, which will probably look, well, I mean, not probably, must look something like this, as this is a basis which spans the vector space of polynomials. You can go back and say this is c1x, c2, half x squared, and so on. And then if you take a derivative of this polynomial, you're going to get this one. So whatever polynomial you want here, you definitely can reach surjective. Now, that's what it means. Yeah, so this one, it definitely also takes quite a bit of head scratching. In fact, at times I think it almost just maybe make me walk into someone in the street, because I find walking in the street to be a really tedious activity. There's too many people around and I don't know how to handle myself. So it's easier to just think about things that are actually interesting to get away from that. And this is one instance where I thought to myself, well, maybe I shouldn't have done that because this problem is kind of weird. So, and not in a good way. So, say you have a polynomial, right? Which is this polynomial p. You want to construct q such that 5 times the second derivative of q and 3 times the derivative of q is equal to p. And you may think, well, this looks like a diff eq problem, so I want to solve it that way. But then, this is linear algebra. This is not diff eq, as the textbook also says. So I've got to think about this in terms of like spaces and all that stuff. So first you want to think. Well, actually, I'm not sure if I even remember the solution to this because it's been such a long time. But initially, what you could do is obviously, not obviously, I keep saying that. You can construct q such that 3 times the derivative of q is p. And how you could do that is by saying something like this, right? Since the map of the differentiation, or the differentiation map, is surjective, for every p there exists a q such that q prime is equal to p. That's fine, right? For some q. But then you just take an r and say that it's equal to a third q prime. So then r prime is going to be a third p, which means 3r prime is going to be equal to p. So that's fine. You just construct yourself a polynomial such that 3 times the derivative of that polynomial is equal to p. But what about this part, right? That part's also weird. And the fact that, these two are not just some separate variables where you could just then break p into half p and half p, and then you can say that there exists some sort of connection between these two individually is annoying, because these q's share the same variable. So in some sense, if you perturb this, then you also change that, right? So it's a bit more complicated than that. I guess that's why they have a class for it, right? Differential equations. But anyways, so thinking about it this way, then you could tell that there's something like kind of eerie about this problem. So maybe you thought, well, let's try an example, because what is there to lose, right? So let's say you got x squared as your q, then your q double prime is going to be, maybe a fancier example, maybe 3x cubed, I don't know, right? Probably more realistic. Then q double prime is going to be equal to, time to demonstrate that I can take derivatives. Amazing skill, yes. So 9x squared, yep, almost didn't do that correctly. And then somehow 5 times 9x squared, 5 times 12x plus 3 times 9x squared is going to be equal to that p, right? And this is almost completely senseless, because what the heck, how did I get there? How do you break it down so that you find that exact q? So maybe the better example is actually working it the other way around. So say you have p equals 2x, how do you construct So the first instinct is that this is actually kind of weird. I'm gonna take a pause here and upload a new video because I don't know how to something like this actually. I may have escaped my mind already. I mean, gosh darn.